All right, that's right. That's right for the delta H of formation of ethanol. Here, compiled in Appendix D are delta H's of formation. These are standard because there's a little superscript there. Standard enthalpies of formation for various things. And these are just alphabetical, so A, aluminum. The standard enthalpy of formation for aluminum solid is 0, as it must be because we're going to form aluminum solid from the element aluminum in its standard state, which is solid. And so this is aluminum solid going to aluminum solid. However, the standard enthalpy of formation for Al3 plus is not going to be 0. Because, you know, if we're going to form Al3 plus, we're forming 1 mole of Al3 plus from the element in its standard state. And so the element is just aluminum solid. And so we're going to go from aluminum solid to aluminum 3 plus. Do you think that's going to be 0 energy? No. I mean, you have to break apart the aluminum crystal, the metal. Then you have to strip electrons, and then you'll have to dissolve it in water because this goes to AQ. And so here we see that delta H of formation for Al3 plus is minus 531. Minus 531 kilojoules per mole of Al3 plus that's formed. Here, AlCl3, if you look at these are all exothermic, and go all the way for aluminum sulfate, we go all the way to minus 3441.
So we have to worry about the electrons?
Yes, we do have to worry about the electrons because, and I'll talk about this one more, because the electrons, where are the electrons? You know, because this is not balanced. When we have a half reaction, right? When we have the half reaction, the atoms must balance, and so must the charge. But in order to balance the charge, I'm going to have to add 3 electrons. The problem is where are those 3 electrons? Are those 3 electrons AQ? Are those 3 electrons gas? Or are those 3 electrons liquid? What do you think those 3 electrons are? Neither. None of those. No, you're absolutely right. This should be balanced, but you know, there's a very tricky thing that happens with this that I'm going to talk about right now. This tricky thing I'm going to talk about, you look at most of these, they're exothermic, and then finally we hit some that are endothermic down here. Go. Here's some endothermic ones. Plus 35.6, 30.91, 1464. We can go through some of the entries. We talked about, did we talk about graphite and diamond?
Yeah. Yes.
Yeah. And so we've got a carbon here. The standard enthalpy of formation of graphite is 0, and of diamond is 1.90. So this would be forming diamond from graphite. But if we go to carbon gas, take a look. Plus 716.7. And so that's vaporizing. Well, graphite's extremely hard to vaporize. Here, this dicarbon dinitride, which would have a different name in organic chemistry. This is 309 plus. And so it looks like we have some negative, some positive standard enthalpy of formation. And the way to understand the negative and the positive and the 0 is taking a look back in the chapter. They have a little figure that kind of shows this, but we don't really use that figure for anything. And so let's take a look at this figure here. Looking at this figure, here are the elements in their standard state. So if you're an element in your standard state, then you aren't going to change because delta H's of formation are formation of the substance from the elements in the standard state. So you're already an element in the standard state. Delta H of formation is going to be 0. So that's what this plane is indicating here. Some things are going to be more stable energetically than the elements in their standard state. So for example, butane, propane, this would be ethene, or no, this is not ethene, this is ethane, ethane, methane. And some things are less stable here. You know, this would be ethene, this would be ethine or acetylene. less stable than the elements. That's the delta H's of formation that are positive versus negative. That's all I'm going to say about that. What we want to focus on is look at the entries. Entries look pretty normal, some endothermic, some exothermic, until we get to the H's. When we get to the H's, then something weird happens. Do you see something weird about the H there? We have 2 zeros. One makes sense. Which zero makes sense? H2, yeah. H2, it's obvious H2 gas has got to be 0 because we're going to form H2 gas from, if we form H2 gas from H2 gas, then there's going to be no change in energy. It's just H2 gas going to H2 gas. Same thing, right? On both sides. So we got 1 mole of H2 gas at 298, 1 mole of H2 gas at 298, nothing changed. However, there is something that did change. The delta H of formation should be 0 for this. But if we form 1 mole of H plus AQ, and this is under standard conditions, what does standard conditions mean again? This little superscript here. I know what formation means. Formation means formation of 1 mole of substance from the element. In this case, the element would be hydrogen. The standard state of hydrogen is H2 gas, so I'll have to take a half mole of H2 gas to get 1 mole of H plus. But that little standard means what? One bar pressure and 1 molar solutions. So this would be forming 1 mole of H plus at a concentration of 1 molar. That's how we'd read that. Anyway, what do you think? Well, we got to break the hydrogen atoms apart. We got to strip an electron away. We expect some energy difference, right? You don't expect these to be the same energy. Do you expect it to be the same energy? Like if you have a cylinder of hydrogen gas, you can easily convert into H plus. H plus and hydrogen gas are the same energy. What do you think? Yes?
Yes.
Well, according to this, delta H of formation is 0. That seems odd, doesn't it? That seems odd. And so this brings up another thing that seems odd is where's the electron? Matter is neither created nor destroyed. The electron has to go somewhere. Problem is free electrons, like is this stable? I just do an electron AQ. Is that stable? Maybe I'll form 1 molar H plus and 1 molar electrons AQ, and the electrons can move about in solution and the H plus can randomly move about in solution. Is that possible? No, it's not. Electrons had to go somewhere. Where did the electrons go? Well, hydrogen is what we call the reducer. The electrons must have went to the oxidizer. So doesn't it matter what the electrons are? Where the electrons went? And so this is the problem with the ions. Can I form H plus alone without any anion? Is it possible to form H plus alone? It's impossible. I can't form H plus alone. I can form a cation, but I need to form an anion at the same time. That's where the electron goes. The electron doesn't go into solution. The electron goes to the other species, the anion. And so this is what we're going to have. Let's say we're going to look at the HCl, AQ. Let's say we're going to form HCl, AQ. When we form HCl-AQ, we can figure out the delta H for this of formation, because this is going to go from 1/2 hydrogen, so a half a mole of hydrogen gas plus a half a mole of chlorine gas. And this will give us, and so this is something we can determine. This is going to come out to minus 167.2 kilojoules. So in this case, we're going to form a cation. You know, we're going to form H plus because HCl is a strong electrolyte. Strong electrolytes are going to have H plus and Cl minus in this case. And so when we look at this, here we're going to form 1 mole of 1 molar H plus and 1 mole of 1 molar Cl minus. The delta H of formation for this is minus 167.2 kilojoules. So the question comes up here. You know what? This is for the formation of HCl, but you know, how much of this energy is associated with H plus? And how much of this energy is associated with Cl minus? That is, can we do you know, is it possible to split this up and just measure the H plus and the Cl minus? No, actually that's not possible. I mean, whenever we form a cation, we've got to form an anion. Both of these are going to happen. And so since we can't just form cations, we can't just measure that. And so I have to figure out how much of this is for H plus and how much of this is for Cl minus, because I have the total. And so in other words, X plus Y is equal to minus 167.2. So this is an example of 2 unknowns, 1 equation so far. We need 2 unknowns with 2 equations. And so we got to think of the second equation so we can figure out what proportion of that energy is from the H plus and what proportion is from the Cl minus. So can you take a minute and think of a second equation that we can use to figure out what X and Y are?
Would it be water? Would it be water? H and H. Would it have to be related to?
Yeah. I mean, how would the H and the Y come in?
Wasn't it aqueous? HCl.
HCl is aqueous.
There's water in it already.
There's water in it. There's water. I know this that some people, when they did the hydronium, some people did hydronium on the test and didn't balance out the waters. There's water present. In fact, this is not H plus. This is hydronium. So I should add a water over here and a hydronium here. What I'm not going to do is it's going to be the same energy. Some people will get different energies because start calculating. Well, anyway, did you come up with a second equation we can use to solve for one of the variables? What happens if I have 2 unknowns and only 1 equation? Is it possible to solve that to a unique solution? 2 unknowns and 1 equation. Well, let me tell you, you can sit there and think for a while, but you aren't going to come up with a second equation for this. We might try to do this theoretically, you know, using the theory of chemistry. But those calculations aren't so accurate. And so what do you think about this? I'm just going to guess. I'll guess that 50% of this energy was released from the formation of H plus and the other 50% was released from the formation of Cl minus. Would you agree? It's a 50-50? No. It's probably biased. It's biased towards what? H plus or Cl minus? Which one do you think is more energy? It's Cl minus. So let's go 70 or 80% to Cl minus and 20 to 30% to H plus. Would you think that's fair? Do you think that's fair? Those are kind of random guesses, huh? And so what a lot of people will say, hey, this problem is impossible to solve, right? Because we have 2 unknowns and 1 equation. We can solve it to some equation, but we aren't going to solve it to a unique answer. So, what are we going to do? Yeah. You know what we're going to do? We're going to do a 100-0 split. This is what's done. So sometimes when you don't know, we'll just do this. We're going to say that 0% is due to H+, and that 100% of this energy is due to Cl-. Does that seem pretty accurate to you? Does it seem accurate? Not at all. This is not accurate at all. And so if it's not accurate at all, why do it? And so this is 0 by definition. It's not 0 by reality. In reality, there is some energy exchange. But by definition, it's just 0 because we can't figure it out, the math. Can't figure out the math. But here lies the trick. The trick is you can never form a cation without an anion. The electron has to go somewhere, and it cannot go into water, it cannot go into gas, and it cannot go into being a liquid. And so we always have to form a anion along with a cation, because whenever we have a reducing agent, we must have a oxidizing agent. Otherwise, the reaction doesn't work. This is why it's called redox. Not like reduction, reduction, or oxidation, oxidation. We have to have an oxidizer, we have to have a reducer. And so here is the fix. The fix is whenever we form a cation, we're off. We're too low, let's say. But whenever we form an anion, we're off. But the good thing is we're off in the opposite direction. And so one error is too low, the other is too high, and when you add them together, they cancel out. Right? And so let's see an example of this canceling out. Let's go ahead and calculate this. That delta H of formation for this, we're going to use the Hess's law variant. Did I already show this? That the delta H of reaction is equal to the sum of nu P times the delta H of formation of the products minus the sum of nu R times delta H of formation of the reactants. Yeah. Did we do this?
A couple weeks ago.
All right. Then what we're going to do here is we're just going to go ahead and do that. What are we forming? We're forming H+. So we're going to form 1 mole of H+, and delta H of formation for H+ is 0 by definition, right? And then we're going to form 1 mole of Cl-. 1 mole of Cl-, and delta H of formation for Cl- is 1 minus 167.2 kilojoules per mole. Then minus the reactants. We're going to form half a mole of hydrogen. What's the delta H of formation of hydrogen, the element? The formation of an element from itself is 0. And the formation of this element from itself is 0. And so 1/2 times 0, 1/2 times 0 is just 0. And so what happens is we have one systematic error pushing it in one direction, the other systematic error pushing in the opposite direction by an equal amount, and those systematic errors cancel out. And so when we add a cation plus an anion, it's always going to come out correct. So what that means is all the cations are off in one direction, all the anions are off in the opposite direction. Does that always mean we're going to does that always mean we're going to have a cation and anion? Yeah, but in some reactions the anion is a spectator. So let me take a look at one of those. So let's take some aluminum solid plus, let's go with 3 HCl. This is going to form AlCl3 plus 3 halves H2 gas. I look at the chart here, and I go, I want to figure out the delta H for this reaction. So do I have everything? So delta H of a reaction is going to equal the sum of the delta H's of formation of the products. And so I need AlCl3. I look over here. Do I have AlCl3?
Yes.
Yes, except there's one major problem.
Solid.
It's solid, and that is aqueous. I can't use it because it's solid. But you know what? If I look at this, this is what we call the complete equation. Then we have the ionic equation, right? And the ionic equation is going to just be Al solid plus 3H plus 3Cl minus yields AlCl3.
3 plus.
Oh, Al3 plus, right. Al3 plus 3Cl minus plus 3 halves H2. And then if I go to the net ionic equation, the NIE, then I'm going to have Al solid plus 3H plus yields Al3 plus 3 halves H2 gas. And then let's take a look at this. If I take a look at this, I'm going to get that delta H of this reaction. I'm going to just use the net. If I use the net, then I got it, because delta H of the reaction is going to be equal to the delta H is the formation of the products, 1 mole of Al3 plus times the delta H of formation of Al3 plus minus 531 kilojoules per mole. Plus 3 halves H2. Well, H2 you should already know it's H2 gas. It's going to be plus 0. Just write 0 here. Minus the reactants. Al solid is going to be
0.
0. And then I have plus 3 moles of H plus. And what's the delta H of formation of H plus?
0.
0 again. Oh, that was easy. And so delta H of the reaction here is just minus 531 kilojoules. Is that right? Because didn't I say we need to form a cation along with a anion, and that the cation leads to an error in one direction and the anion leads to an error in the opposite direction, but here I just have 2 cations. So if I had just 2 cations, then does it still work? No? Because it seems like it just pulled the error in one direction and the same in the other direction, right? And so does it? If it doesn't work, maybe we should go back to this. Does it work? It turns out it does work in this case. It does work because if we factored in the anion, we got 3 moles of chloride here at minus 167.2 times 3. And then 3 moles of chloride here at minus 167.2. And so that's going to be, this is going to be positive, the products, minus the negative of the reactants. The chlorides would have canceled out anyway. Even if we factored in the anion, they would have canceled out. And so why does it work in here when the anion cancels out? Don't we need the anion to stay in there to pull the systematic error back? We don't. The reason we don't is because we aren't forming 2 cations on the same side. We're forming 1 cation on the left the one cation on the right. So if this one pulls it this way and this one pulls it the same way, they're going to cancel because it's products minus reactant. And so if this one had, let's say, a minus 10 pull this way, and this one had a minus 10, well, it's going to be minus 10 plus a minus 10, which is, oh, actually, no, minus 10 minus a minus 10, which is 0. So it cancels out in this case, too. Do you see? It's because it's on both sides of the equation. And it cancels out like spectators. You have a spectator error, systematic error, that would cancel. Does that make sense? Anyway, the equation's balanced. As long as the equation's balanced, you're safe. You don't have to worry about it. Okay. All right, so we can do delta H's for any reaction as long as the data is in here. And this beats doing calorimetry for sure, because it's much easier. All right, now what we're going to do is we're going to do an example. Once we have delta H, then we'd like to use it, because this is minus 531 kilojoules of energy released, or actually 531 kilojoules of energy released for every mole of aluminum that react. So if I have 2 moles, it would double that. And so this delta H is very useful for us because delta H is going to tell us the net energy that we have to input or the net energy that we're going to get out from this particular reaction. Is that mine? All right, now let's take a look at this problem here. Although some people have already done this, I just wanted to talk about this because I know Z did this, right? The climbing mountain. Did anybody else do the mountain climber? No. All right, we're going to do this. We're going to look at the metabolism of glucose, C6H12O6. Okay, when you metabolize glucose, glucose is a carbohydrate or sugar. It's a solid white crystalline substance. And so you eat this stuff and then you inhale oxygen. And then it undergoes metabolism. In metabolism, there are a whole bunch of steps in metabolism called metabolic cycle. So it undergoes a whole bunch of steps, and then eventually you exhale the CO2 as gas, and you produce some water and energy in addition to this. And so this would be complete metabolism of the glucose. In other words, this is a redox, so we're completely oxidizing the glucose. Glucose is our fuel, oxygen is the oxidizer. Completely oxidize it. And so this is going to give us 6 oxygens, we'll just balance that, 6 carbon dioxide, and same for water. And then we think about this. This looks awfully familiar, doesn't it? What kind of reaction does that look like? This is combustion. And so, yeah, a lot of people, when they think about this, okay, they think they're going to burn some sugar in your body, but there's no flame that results in this. And so it really isn't combustion in that sense, but it is in the sense that the reaction looks in fact, the reaction looks the same. And so let's take a look at delta H for metabolism, which is our delta H for reaction here. And the thing is this the same as delta H for combustion? If we were to burn the sugar, which this reaction does look like, would we get the same amount of energy as metabolism? Or would we get more energy, less energy? What do you think? It turns out we would get the exact same amount of energy. Because delta H is a state function. It being a state function, it doesn't matter how it gets there. It just matters what the final state is, CO2 and water, versus the initial state. And when we look at the initial and the final state, they're the same as combustion. The only difference is biochemists prefer a different temperature. You know, chemists prefer 298 Kelvin. Biochemists usually use body temperature. And so you'll see a lot of data, you know, for us, we just do delta H of combustion at 298 Kelvin. Well, they'll do it at a little higher temperature than that. That would give a little bit more accurate value. But it's not a big difference, so we'll just go ahead and just assume it's the same. The same. The same.
Yes, sir.
Uh-huh.
So what you're saying is that our body is as efficient as burning fuel, like actual combustion?
What do you mean as efficient?
So when you burn gasoline in a car, it's not 100% efficient. Like it doesn't transfer 100% of the energy.
To
from the
what?
gasoline to the car.
Well, where does the lost energy end up? Heat.
That's the physics.
Or heat. I guess it would be.
Well, in that sense, it's 100% efficient because all the potential energy was converted into.
I mean efficiency in moving the car. So
Okay, in terms of how much work you do. Well, why do you think burning gasoline is efficient? If I took a trash can and filled it with gasoline and burned it, am I going to convert all that energy into work efficiently because I'm burning gasoline? Is that how it works?
So what you're saying, it's going to convert the same amount of energy to move a human body as compared to
I didn't say it's gonna. I didn't say it's gonna convert all that energy into moving a human body. I'm just saying that the total energy that you're gonna get is the same. Yeah.
That was my understanding.
Okay. But the tricky thing is, and I know where you're coming from because you're thinking, you know, it's like my slide example. Remember the slide example I showed you with the pulley? You know, that was a hypothetical slide because is there really a frictionless pulley? You know, and not only that, well, this person would have to go infinitesimally slow because there's going to be friction with the air molecules as they're coming down the slide because, you know, and so they have to be going, and then there's going to be friction, you know. So even though I said we're going to convert all this potential energy into work, it isn't all converted into work. You know, and the thing. But that's a different story. We don't care about that because all we care about is not how efficiently we convert that energy into work. What we care about is how much energy we get. That's it. Because somebody can always come up or try to make a more efficient machine. So for example, somebody will try to come up with a better bearing with less friction and to make it more efficient. But we don't want to worry about that because that's something somebody else can do. What we want to worry about is what the total usable energy for this is. And that's what the delta H is. The delta H, we don't have to worry about the tax, bonus, whatever. This is the amount of energy we should get as long as we do this under conditions of constant pressure. So if we do this under constant pressure, this is the total. Now, what I can do with that is I can just leave that all as heat. Or I can try to convert this energy into work. And so what I call this is the usable energy. I just briefly mentioned that. This is the usable energy because we couldn't use some of that other energy. We couldn't use some of that other energy because that was the natural work of a chemical reaction. And so when we're looking at that, when we have this as the natural work of the chemical reaction, fine, but we don't have to leave it like that. This is the natural work of the chemical reaction. We could try to do more and more work, which would shrink down the heat. So, regardless of how the body uses it, and it depends on how the body uses it. You know, is it going to use it to make storage, energy storage molecules? Is it going to use it to for muscles, or is it going to use it for brain activity? regardless of how it uses it, this is the amount of energy available to use. That's all. And the amount of energy that's available to use is the same whether we burn it or we metabolize it, because there could be many steps here, up and down, whatever. But if we end up in the same place, and we start off at the same place, then it doesn't matter how it gets there. Another example, and this is what you might be thinking, is let's say I had a delta T equal to plus 10 degrees C. And you go, wait, doesn't it matter how efficiently that happens? So for example, if I went from 0 degrees C to 10 degrees C, boy, that's efficient. That's really efficient, right? And you go, wow, that's really efficient, 0 to 10 degrees C. Compared to this, if I went from 0 degrees C to 2,000 degrees C, and then I went from 2,000 degrees C back down to 10 degrees C, you'd go, wow, that's terribly inefficient. Terribly inefficient. And therefore, the delta T should be different. Right? Are the delta T's different? This is T final, 10 degrees C. This is T final, 10 degrees C. This is T initial, 0 degrees C. This is T initial, 0 degrees C. Are the delta T's different? The delta T's are exactly the same. And so we aren't answering the question about the path that this takes. We're just looking at the energy that's involved in the difference here. And so, anyway. And so what we want to do is we want to know what delta H for this is. Well, delta H, all we need to know is the delta H of the formation of the products minus the delta H of the formation of the reactants. This will save us the calorimetry experiment. If we had to do calorimetry, what type of calorimetry would we do? Would you burn the sugar in a coffee cup? Well, we probably wouldn't do coffee cup calorimetry. We probably have to do bomb calorimetry. But if we did bomb calorimetry, are we going to get delta H directly? No, if we did bomb calorimetry, we would get, instead of delta H, we would get what? Delta U. But we don't have to do any calorimetry because all we need is Hess's law using formation reactions. Hess's law using formation reactions is easy because we just look at the product, 6 moles of CO2, and then we go and find the standard enthalpy of formation for CO2. There are a few more things I want to talk about with this problem, so just bear with me. You've already done it. All right, so we have CO2 here. It's minus 393.5. Minus 393.5 kilojoules per mole. We got 6 H2O liquids. 6 moles of H2O liquid. H for hydrogen, so let's go to H. And then look up H2O liquid. Minus 285.8. We have to be careful because there's H2O solid there as well, and H2O gas, I think. So minus 285.8 kilojoules per mole. Okay, minus the reactants. The reactants are going to be C6H12O6. C6H12O6 glucose. Let's go to carbon C. When I look at C, I don't see it here. And one of the reasons is because the glucose is considered an organic substance, whereas these, like carbon dioxide, are considered inorganics. The organics are in a separate table at the back. And so let's flip to the back of Appendix D. and we look at the organic substances like methane, ethane, propane, butane, methanol, ethanol. We get to the end of the table, and there's no sucrose here. And so they didn't give us the data for the sucrose, but go back to the problem. Let's see if they gave it to us in the problem. And they did. In fact, a lot of people mistake this for the delta H of combustion. Is this delta H of combustion of glucose? No, this is delta H of formation of glucose. And so a lot of people will accidentally put, well, delta H of metabolism, that's just given as minus 12, 73.3. Minus 12, 73.3 kilojoules. But that's wrong. It's not. That's delta H of formation for glucose. We're forming 1 mole of glucose, C6H12O6. Solid. And that's going to cost us minus 1273.3 kilojoules per mole. And then how about O2? O2 is 0. And so let's go ahead and calculate this here. What is the delta H for this reaction? All right, so 6 times 393.5. Six times 285.8. Okay, and 1273.3. And we get this. I get delta H for metabolism, which is equal to delta H of combustion, minus 2802.5 kilojoules. What do I want? Let's say, what if you had an iron stomach? Let's say you had an iron stomach, it doesn't expand, it doesn't contract, it's fixed volume. Although that's not the case, but maybe in a cartoon it would be the case. So if you were to metabolize this under constant volume conditions, will you get the same amount of heat, less heat, or more heat, or more energy? You know? You might try to do that. Keep the volume constant if you can get more energy from that, right? What do you think? Well, it depends on the volume change here. But if we do just rough volume, then solids and liquids have small volumes compared to gases. This gas is about 150 liters to 150 liters. It looks like it's not worth it to keep constant volume because you probably get the same amount of energy, roughly. So, don't. Well, anyway, okay, this is the amount of energy we get per mole of glucose. Let's continue the problem here. Heat released in the process. So this is the energy. This is a usable energy. And so all that energy that's released in this process can be converted into work. But here's where we talk about it. It turns out that it's only 70% efficient in converting that energy into work. And so we can't convert all of that into work, which would be great. If we converted all of it into work, then we could do a lot more work. But your body also needs heat as well, so it's not bad to have 70% converted into work and 30% as heat. And so, okay. And so out of that many kilojoules, we've already worried about the work. And so what we're trying to do is we're trying to get additional work out of this. And so we know that delta H is equal to delta U minus the W. We already have the natural work of a chemical reaction here because this is delta H. But what we're going to try to do is we're going to try to eke out more heat out of this. In other words, this is Q minus W, and so we try to grow the heat, or actually shrink the heat and add some more work. And so we're going to add some more work to this, not just the natural work of a chemical reaction, we get less heat. All right, so let's calculate the mass of glucose metabolized by a 58.0 kilogram person and climbing a mountain with an elevation gain of 1,450 meters. Assume that the work performed in the climb is about 4 times that required to simply lift 58.0 kilograms by 1,450 meters. And so there's some kind of mountain here. It's 1,450 meters tall. And then there's a 58 kilogram person over here who's trying to climb this mountain. 58 kilograms. And so how much energy is it going to cost to climb that mountain? And so what we need is, we need to figure out what that is. And so if you've had some physics, then this is not difficult, because the amount of energy is equal to from physics. It turns out the minimum amount of energy is if this person just was pulled straight up. If you pull this person straight up, some kind of frictionless pulley system or whatever else, right? Some kind of elevator system, then that would be the minimum rather than trying to zigzag up the mountain, right? Just one straight shot up would be the shortest distance. And so if we do a straight shot up, then in physics, do you know how much that would cost you? And so this would be the minimum amount of energy. Minimum amount of energy required. The minimum amount of energy required will be equal to the mass times, well, they're fighting, what are they fighting climbing a mountain? They're fighting gravity. So mass times gravity times how high the mountain is. The higher the mountain, right, the more energy it's going to be required. And so the minimum amount of energy required is mgh. But, how are you expected to know? This is not a physics class. Well, how you're expected to know is you try to take advantage of what the book has to offer. And a lot of people don't do this. A lot of people don't look at the everything the book has to offer. And so let's take a quick tour of the book here.
Isn't that the same as work famous distance and stuff?
Yeah, right. Exactly. This is the same as work. All right, so it turns out there's other useful things in this book, other useful resources. In Appendix A, we have something called the math review, but it's not all review. And so in Appendix A, we have exponential arithmetic. This should all be review. I hope addition and subtraction. Addition and subtraction is review, right? One paragraph on that. One paragraph on multiplication. I think this is getting a little, well, actually it's not so simple because it's addition and subtraction in scientific notation. So it isn't as obvious as you might think. Division using scientific notation, multiplication using scientific notation, exponents, logarithms. All right, so yeah, that's pretty good. Sig figs in logarithms. Oh, that's pretty useful. Natural logarithms, algebraic operations, the quadratic equation. It's probably been a while since. The quadratic equation, you'll see this more in Chem 1B. So everything's familiar so far, right? But how about this? Do you know this? Is that familiar or is that new? This is new? All right. The method of successive approximation. So everything in there is review except for the method of successive approximation. So what is the method of successive approximations? Has anybody heard that before or used it? The method of successive approximations. The method of successive approximations, and it's a page and a half of this, is a very fancy word for something you might have done already. And so they're going through an example of the method of successive approximations right here. And basically, the method of successive approximations is a fancy word for the guess and check method. Have you used the guess and check method before? Everyone? Or not everyone? Let me give you an even simpler example that's not going to take a page. Here, let's say 2x is equal to 6. And so if you don't know what the answer is, you guess. So I'm going to guess that x is equal to 1. If I guess x is equal to 1, then I plug in 1 here and I get 2 equals 6. Is that correct? No. And so then I'll guess, I'm going to guess x is equal to 4. If I guess x is equal to 4, then I get 8 is equal to 6. That's wrong too. And so should I go bigger or should I go smaller? I should go smaller. I'm going to go x equals 3. And I'll get 2 times 3 is 6, which is equal to 6. And I got it. Only 3 guesses it took. So that's the guess and check method. Graphs is nothing too new. Dimensional analysis. This dimensional analysis, what's the difference between this dimensional analysis and dimensional analysis in Chapter 1? This one has some more of these squared and cubed conversion factors, like square inches to square feet, this kind of stuff. More so than Chapter 1. And some more practice here. That's Appendix A. Appendix B is a little physics review. Or maybe it's all new if you haven't had any physics. This is physics. And so if we look at Appendix B, B1's velocity and acceleration. Velocity is speed. We've seen that before. Speed was equal to, what was it? Square root of 3 RT over molar mass. You remember that? URMS speed. We have force and work. Turns out these are all Newton's laws. Force and work. So if we take a look at this here, force is the mass times like gravity, which is gravity is called acceleration. Force is given in units of newtons. If we take newtons and times it by meters, we get work, because a newton times a meter is a joule. Newton is a kilogram meter per second squared. So a kilogram meter per second squared times a meter is going to give you a kilogram meter squared per second squared, which is joule. And so this is where that equation comes from. We do work of climbing that mountain is equal to the mass times g, which is this F, times the distance, or the height, which is still mentioned, 1,450. And so this is the work in climbing that mountain here. We have energy, the same thing, except they call it A for acceleration, but we're fighting gravity there, which we called it G, mgh. The work. Kinetic energy at the bottom, 1/2 mu squared. We've got magnetism here. In B4, static electricity. Do you recognize this equation? This is the equation I talked about in Chapter 1, but I didn't put in 4 pi epsilon. I just put in Q1, Q2 over R squared. Do you remember this one, or D squared? What's this one called? This equation's called Coulomb's law. So here's Coulomb's law. You can read about it in more detail than I talked about it. I didn't want to talk about the physics too much. I skipped 4 pi epsilon, what that means. We also have current electricity. This is more for Chem 1B. We have electromagnetism, etc. Then we go on to Appendix C. Appendix C are the SI units, or the metric prefixes. So femto, atto, giga, tera. Derived units, which are from the base units. Here we can see the definition of the joule. The joule is defined as a kilogram meter squared per second squared. See the definition of a watt. A watt is a joule per second. A newton is a kilogram meter per second squared. A volt is a joule per amp per second. There's other ways of expressing a volt too, which is a coulomb. Times coulomb. This table I don't really like so much. C4. You take a look at table C4, the heading. Units to be discouraged or abandoned. One of these units I really like, the angstrom. You know why I like the angstrom? Because atoms are like 1 to 6 angstroms in diameter. It's an easy number to remember. And so I really like angstroms. But I'm supposed to discourage you from using angstroms. There's another unit I really like on this table, too. Do you see it? I can live without torr, but I like torr. I like millimeters of mercury, but I really like atmospheres. So I'm going to be one of those holdouts, that will continue to use atmospheres. Anyway, so the world is changing. I'm just not changing along with it very fast as people go to bar. All right, so you should take a look at this. This is sometimes it's helpful. But anyway, let's go back to this problem that we're doing. And so that's the minimum amount of work. But do you think the person's going to climb up the mountain using a pulley system like that and being pulled straight up? No, they're probably going to zigzag up the mountain. If they're going to zigzag up the mountain, then it depends on the path they take. And so we're just going to guess. We're just going to take a wild guess. This is a wild guess. The wild guess is this. Whatever the minimum is, we're going to assume that the work performed in the climb is about 4 times that required to simply lift 58 kilograms by 1,450 meters. And so first, let's go ahead and calculate the minimum amount of energy. The minimum amount of energy is 58 times 9.8 meters per second times 1,450. That gives me the minimum amount of energy is 824,180 joules of energy to climb that. But we figure it's going to be a circuitous path. It's probably going to require more than the minimum. And so what we're going to do is we're going to assume energy required equals 4 times the minimum energy. And so let's go ahead and multiply this by 4 times 4 gives me 3,296,720 joules of energy to climb. Or probably want this in kilojoules. This would be 3,296.7 kilojoules of energy. And so we need this amount of energy to climb. And all that energy is going to come from metabolism of glucose. And so what this is going to do is it's going to turn into a dimensional analysis problem. Now, there are different ways we can handle this. we could do a system in the surroundings here. You know, for example, the surroundings might be, or the system might be this energy, and all that energy is going to come from the surroundings. The surroundings might be this, the reaction. But oftentimes we don't do that. Once we have a delta H, we just use stoichiometry to figure it out. And so this is one thing we have to be tricky. Excuse me, that is a little bit tricky. We're going to need 3,296.7 kilojoules required. We have to worry about the efficiency. Remember when we were talking about limiting reagent? If you have a party, you need 100 cookies, right? You better bake some extra, right? Because you might lose some, or some might break, or whatever. Well, we already know we're going to lose some of this energy. We aren't going to have all this energy in the form of, all right. And so what we're going to need, we're going to have to bake extra energy into the equation. And so we're going to have to bake in for every 70 kilojoules required, we better bake in an extra 30, and so we better get 100. That way we can lose 30, right? And so this will be 70 kilojoules required. Requires a total of 100 kilojoules. And so we're going to need more glucose, right, than expected. All right, and then here, we're going to say, okay, there's negative 2802.5. Oops. I need to flip this. For every mole of glucose, C6H12O6, there's negative 2802.5 kilojoules. And then I want to know how many grams. And so glucose, I know the molar mass of that is 180.18 grams per mole. And so how many grams does this come out to? So that's 3296.7 times 100 divided by 70 divided by 2802.5 times 180.18. I'm going to need, I must have screwed this up. Does that sound right? 303,000 grams of glucose? 303, that's a big pack of glucose. But 300,000. 300,000. Yeah, I guess you can just eat your way up. Climb a mountain of glucose. Yeah, obviously that's got to be a mistake. So let me redo that. 3296.7 times 100 divided by 70 divided by 2802.5.
That's 2,800
times 180.
That's grams, right?
0.18. Oh, this is better. I'm going to need negative 302.79 grams.
Negative.
Oh, yeah.
That's how much you use.
Oh.
Yeah, it is negative.
Is it negative?
It is negative.
Well, this is. Oh,
It doesn't matter.
grams.
Because of negative.
Yeah, can you have negative grams? Does that make sense? Well, you know what? We can't have negative energy either. And so there are two ways of interpreting this negative. One way is we could set this up system and surroundings, which we'd have to do to get rid of the negative sign. The other way is we'll just get rid of it manually. Rather than saying negative here, we'll just say 2802.5 kilojoules lost, evolved, released per mole. And so, you know, energy is always positive. And so then that's going to flip this into positive 302.79 grams. There's no such thing as negative, right? Grams. And so I just need 303 grams of glucose, assuming I did the calculation correctly. 70% of the energy from that 303 grams of glucose is going to go into work. 30% of the energy is going to go into heat. Are we good with this problem? And so you might look at your, can you buy glucose at the store? They sell it in bulk? Do they?
You can get it
I don't want to hassle with going to buy glucose. What if I used sucrose? You know what sucrose is? Sucrose is but you know what? A lot of ingredients, they don't tell you what the sugar is because they classify all the sugars together. Is that fair? They say carbohydrates. Carbohydrates, well, you don't know. Is that sucrose? Is that fructose? Is that glucose? What is that? They just say carbohydrates. Carbohydrates is an organic class of compounds that are all sugars. So if I have carbohydrates, well, how many grams of carbohydrates do I need? Well, we're in luck. Do you know why we're in luck? Because most of the carbohydrates have about the same amount of energy per gram. In fact, in bio, you'll learn that the carbohydrates, carbs, have about 4,000 calories per gram. 4,000 calories per gram.
Little calories, but no.
Yeah, except working with these big numbers is a hassle. So food, yeah, in terms of food calories, it would be 4 calories per gram. A food calorie would be the big C of the capital C. The chemical calorie would be the C. And 1 food calorie is 1,000 regular calories. And so carbs have about the same energy per gram, whether it's sucrose, glucose, fructose, because they have similar structures. What else? Proteins. Proteins have about the same too. Do you know proteins have roughly 4 calories, food calories per gram? But fats have higher. Is it 10 or 9? 9 calories per gram. And so these are fuel sources for metabolism here. And so we can see. Is this going to take place at constant pressure or constant volume? Constant pressure.
Oh, they're just an assumption. There's 4 times more energy. Could they assume to go straight up?
But if we did this at constant volume, what would the energy be? I know it'd be about the same, right? Roughly. Because even Petrucci says something like this. Petrucci says, if we go back to the xylose problem we did earlier, I didn't mention this earlier, but Petrucci says this: assume for this reaction that delta U and delta H are about the same. So the amount of heat you get at constant volume is about the same as the amount of heat you get from constant pressure. We could do the same here, but when you say that the difference is small, the difference is going to be small, probably. Somebody's going to ask you, how small? This is the obvious question, how small? And you're going to say, well, very small. And then they might ask you, well, how very small? Well, then you might say, well, my Chem 1A instructor years ago told me it's very small, and I just remember that, and I believe that, right? That's not going to work for an answer. They're going to want, well, if I do ignore the solid and the liquid, how big of an error am I introducing?
Less than 1%.
Less than 1%. Well, are you sure about that?
Yeah.
Positive? Okay. What about all you other people? Could you confidently say that there's going to be less than a 1% error? Yes? And you can argue that no matter how much they press you, no matter how much they disagree with you, they say, I don't believe that. I think it's going to be greater than 1%. You're willing to stand your ground. right? Well, probably the best thing to do is not just take somebody's word for it, but at least do one calculation. Let's try to do one accurate calculation and then see if it makes any difference at all. But you know, this time I'm going to try to go super accurate, because what I'm going to do is, let's take a look. We're starting off with glucose, C6H12O6 solid, plus 6 O2s, gas. And then we're going to go to 6 CO2 gas here, plus 6 H2O liquids here. And so I'm going to factor in, you know, the density of glucose is easy to find. Glucose has a much more stable density than naphthalene. Naphthalene kind of expands and contracts like mothballs. But glucose is a much more compact, crystalline solid, and so you don't expect these large fluctuations in density like naphthalene. And so let me just quickly take a look at the density, glucose density. I think it was 1.54. Yeah, so glucose, we know the density of this, so we can just go ahead and do the calculation. It's 1.54, so it's 1.5 times the density of water, roughly. And then we know, well, O2, right? O2, that's about 25 liters, but this is at 1 bar. So at 1 bar, it's 24.8 liters, right? But you know what? That's assuming it's an ideal gas. Because then we got to think, is O2 just as ideal as CO2? What do you think? Or is one more ideal than the other?
Oxygen is ideal.
Would you say they're equivalent in terms of ideal? Actually, they aren't. They aren't. This is something I skipped in chapter 6. I skipped it because I thought, we don't care, because in all Chem 1A, you know, in all of Chem 1A, we treat gases as being ideal. And we're just going to use ideal gas law, even if they aren't equally ideal. Like, I know CO2 is less ideal than O2, but I don't care, because I'm just going to treat them both as ideal. But now I want to do a more accurate calculation. Since I want to do a more accurate calculation, I'm going to flip back to chapter 6. And let's take a look at the van der Waals equation. If we go back to the van der Waals equation, the van der Waals equation basically takes the ideal gas law, PV equals nRT, and then puts two correction factors on there. The first correction is a correction to the pressure. And so we look at this one, P plus N. N is the number of moles. We just happen to square it. Don't worry about that. V is the volume. We square that. But A is something new. Do you know what A is? A is what we call an empirical correction. And A is something that that depends on the substance itself. And so let's take a look at A. For an ideal gas, A is equal to 0. If A is equal to 0, then that whole term drops out and we're just left with P. Here. Yeah, this whole term drops out, we're left with P. If A is not equal to 0, then it's not ideal. And so let's take a look. Which species has an A closest to 0? Helium. Helium is the most ideal gas on this list. Which species is furthest from 0? Not hydrogen. The hydrogen is 0.2. Looks like this is 9.39. Propane. There's things that are even less ideal than propane. But propane is the least ideal species on this chart. Where's oxygen and where's CO2? Yeah, CO2 is in the middle. Oxygen's closer to ideal. Right? CO2 is a little less than ideal. All right, what does that term do? Let's take a look at this term here just as its impact. As A grows bigger, this term grows bigger. As this term grows bigger, then the pressure has to grow smaller to compensate. And so this term grows bigger, this term grows smaller. So in other words, as A grows bigger, the pressure goes down. The physical interpretation of that is this. A is due to intermolecular attractions. The stronger the intermolecular attractions, the bigger these orange arrows are going to be. I mean, the more force of attraction we're going to have. And so what that is going to mean is these are going to pull this one back. If this one gets pulled back, it's not going to strike the wall with as much force. If it doesn't strike the wall with as much force, the pressure is lower. And so in other words, the stronger the intermolecular attractions, the lower the pressure because of these other interactions preventing full collisions. Does that make sense? And so the bigger the A, the stronger the intermolecular attractions. But there's two corrections. The second correction is for the volume. And it's N, the moles, times B, the correction factor. As B grows bigger, what happens to the volume? The volume's got to shrink smaller. And so as B, or no, is that right? As B grows bigger, yeah. And so, in other words, what happens here is this. If you have 1 liter of gas, that 1 liter is an empty space. That 1 liter is occupied by the gas particles themselves. The smaller the gas particles, the more ideal. The larger the gas particles, the less ideal. And we can see this is going to have a significant impact at high pressures and small volumes where a lot of the space is taken up by the particles themselves. And so let's take a look at the correction factor B. Ideal gas particles have 0 volume, and so B is 0. But you can see this is the volume in liters of a mole of particles. And so, again, helium is the smallest and propane the largest. So propane's going to deviate. And so this is what we're going to do. I'm not going to use the ideal gas law. I want to go for accuracy this time. And let's just go ahead and do it. Actually, which gas deviates more, O2 or CO2? CO2. So you know what? I'm going to calculate this one first. And so let's go with this one. This is going to be V initial up here. This is going to be V final, but I'm going to do this calculation first because this one I expect to be the biggest deviation from what we've been calculating so far. What we've been calculating so far is we just do it. 6 moles times 24.8 liters per mole at 1 bar, 298 Kelvin. We got it, right? That's like a 10-second calculation. But this one we're going to go for this. So, pressure plus N squared A over V squared. You don't have to have this equation memorized. V minus NV is equal to nRT. And let's go ahead and plug in the numbers here. The pressure is 1 bar. So we're doing this under standard conditions. N is 6 moles of CO2. V, I don't know what that is because that's what we're calculating. A, for CO2, let's find out what that is.
3.6.
Yeah, it's kind of in the middle, right? Do you see that? Not on the high end, not on the low end. Sort of in the middle, closer to ideal. 3.658. A is 3.658. There are units for this, but you know what? I'm going to ignore the units. You can see the units there, bar, liter squared per mole squared. N is the same over here. B is equal to, for CO2, B is equal to 0.0429. There are units for this too, but you know what? I'm going to ignore the units. As long as I know I'm in bar, liters, Kelvin, I'm okay. All right, now what we're going to do is we're going to solve for V. Solve for V. Okay, can you solve this for, how much time do you need to solve this for V, the volume? Would you say you could solve for V in about 5 minutes? Okay. All right, solve for V. I'll give you 5 minutes. Five minutes is kind of long because if we just use the molar volume, we could do it in like 5 seconds, right? 10 seconds. But we want accuracy. That's why we're going for it. We're going to go for the ideal, not the ideal. We're going to go for the real gas using van der Waals. Going to solve for V. Okay, so what we'll do is I'll give you 6 minutes because I'll give you 6 minutes and then let's go on break for like a little bit and then come back.
Temperature, we don't do.
Oh yeah, temperature. I forgot to write the temperature. What's Appendix D data? What's the temperature for Appendix D data? 298 and 0.15 Kelvin. 298.15 Kelvin. If you look in biochemistry books, you'll see that the data is under standard conditions, but at a different temperature. Oh, you'll need one more thing, huh?
The R value.
Yeah. Well, the R value, we'll just use our standard R. The standard R, because most people have this memorized, 0.08206 liters times atmosphere per mole Kelvin, and then we're just going to convert it into bar. 1.01325 bar per atmosphere. All right?
What's A's unit? What's A?
A's units? Okay. Let's take a look at the units for A. 1.01325. That'll convert the R gas constant in atmosphere to the R gas constant in bar.
think I got this review. I did it in my head, so I don't know. I should isolate them.
Should be to the third. Yeah, isolated.
How could you get it?
Because there's a B squared.
No, no. So, I divided by this one first, and I divided over this one, and I subtracted. Together would be over this. So what is this? Yeah, you could do that too.
There's two B's. There's a B minus
Oh, yeah.
B squared.
And I took it back out. Oh, no, no. Then I subtracted it. Then I took it. No, I didn't.
All right, I guess your 6 minutes is up. Do you have the answer? Oops. I guess I left this on, so sorry. You got the volume? I'm sorry, can you repeat that then?
I got 1.11 liters.
1.11 liters. If you got 1.11 liters, that means real gases are tremendously different than ideal, because ideal, it would be about 150 liters. So if we got 150 liters, and then we're at 1.11 liters, that's 149 liters difference between an ideal and real gas. So, does that sound about right? No, it's probably calc error. Did somebody else get a different answer? How much more time do you guys need? 10 minutes. 10 minutes, that'd be 16 minutes for one simple algebraic calculation. Shouldn't this be simple?
No. I think it's. I hope it's.
Yeah.
Well, rather do calculus than this.
I know what.
Come on, this is, yeah, for you calculus people, right? This is just algebra.
Why?
Did I tell you about the story of when I took the algebra test?
No.
Yeah.
I said, yeah,
You know, I took years of calculus. I took like 2 years of calculus, and then I had to take the GRE algebra test, so I didn't even study for it. I thought, oh, it's going to be so easy. It was all multiple choice. This is what got me thinking about multiple choice, because I got fooled left and right in multiple choice. And
Is that why you give us multiple choice?
right. There's definitely a skill in multiple choice test taking that you need to develop.
Like,
I'm just gonna get the video of these somewhere.
Like picking the best answer.
And then one of them comes out, and then you flip it. Well, it did have it right the first time.
But sometimes it isn't so easy because you see, oh, A looks like a good answer. I'll pick that one. But it turns out there was a better one later on.
P doesn't have a B.
Is that how you grade us? Yeah, you think this guy could get A. So.
Was that a good laugh, Professor?
Yeah, that was good.
Let's make wild guess. So it's like the P or A.
Maybe you should move one plus round to the other.
Yeah, well, you can't just move it. You gotta pick
Oh yeah. So since we don't have
Can you just take the inner book?
Alright, just let me see if I got the fish. If I'll
Yeah.
Derivative?
Everything else? No.
That was too small. Yeah.
because I got 26.
Oh, raising up. Wasn't all that. To me, the hardest part is when you remember it in like different ways. I'm gonna just go for one test. If I don't get it, I don't know.
The test
Well, he can kind of tell you, but you did a very important
we definitely don't get 3.
No.
Okay, 11 minutes.
How about getting another question?
11 minutes. Have you given up yet?
Of course not. The team spirit?
All right. How many more minutes do you think for success?
The same stuff. You erased everything? Yeah, because 1.1 is too small.
1.11, I'm guessing, is too small. 1.11 is too small because
Yeah, just use perfect. Ideal guess law to cover it. You don't get roughly that. That will not be 1.1.
yeah.
I got 1.1.
Remember, you can cancel it. You can something like this, like whatever.
Yeah, calculate my equation. My equation is right.
Maybe plus or minuses. Sorry.
Yeah, because that's like the last English.
No, this is whole English. You can find it, you can find it.
There's no way white could.
You have to take one day one. You don't have to take 5 transfers. And like.
Calculate.